Welcome to the third lab of this semester. Today we're going to talk about the compressibility of soil. It is important to address the compressibility of soil because in terms of engineering design, you have to evaluate whether the soil will have a sediment when you construct your building at the site. So in today's lab, we are going to evaluate several parameters that are associated with the compressibility of soil. For example, coefficients of consolidation, coefficients of compressibility, and then coefficients of volume compressibility, etc. Okay, so we will perform an experiment for that. And then, so what we're going to do now is to talk about the principle behind this lab. So first of all, from your soil mechanics class, you have learned that soil is basically a three-phase system. Suppose that if I consider saturated soil, so I only have solid and water, okay, in my system. For simplicity, if you have applied loading on this soil system, what you would expect is there would be sediment. Okay, so there would be sediment of this soil system, and then depending on the type of sediment, you may observe that there would be outflow of water out of your soil system. From your soil mechanics class, you may have learned that in geotechnical engineering, we have classified or divided the type of sediment into three main categories, which are immediate sediment, which occurs right after you apply the loading, and then also primary consolidation, which deals with the expulsion of water. And then the third type of sediment would be secondary compression, which occurs after the increase in water pressure ceases, and then it may be due to plastic deformation of soil. So there are three main types of sediment. In this lab, we are mainly deal with primary consolidation. So we are going to evaluate the parameter that is associated with primary consolidation. And then we will make use of the principle that is based on Terzaghi's consolidation theory to come up with those parameters. So let's look at this second graph. So why do we need to consider compressibility? Again, because we want to evaluate how much sediment that we would expect if you apply certain loading to your site. Okay, and then there are several issues associated with sediment. First of all, depending on the hydraulic conductivity, which you determined from last week, the rates of sediment may be different depending on the type of soils you have. As you remember from your class or from your lab, if you have sandy soil, okay, the hydraulic conductivity is large, meaning that water pressure can dissipate very quickly. So what you will expect is the sediment will occur and end very quickly, okay, maybe within hours or days. Okay, but for clay, if you remember from last week, the hydraulic conductivity is several order less than the hydraulic conductivity of sand. In real construction, what you would expect, it may take months, years, or many years, tens of years for the consolidation to complete. Okay, so as what you would expect, your buildings will be used for like 50 or 100 years, depending on the type of building you have. So you do not want the sediment to affect the behavior of your building for such a long time. Okay, so one of the issues that we have to deal with is the sediment. Okay, sediment takes a long time to complete if you have clay material. And then the second issue that we have to deal with associated with sediment is that sometimes because you have heterogeneous soil deposits, or if you have different amount of loading applied on different regions of your sites, what you may encounter is differential settlement. Okay, so it would be a huge issue. Okay, if you have differential settlement, your building may be tilted. Okay, and then there may be damages induced to your buildings. Okay, so differential settlement is another issue that we have to deal with. In Taiwan, we also have regions that is susceptible to settlement. For example, in the Jiayi and Yunlin area, okay, because of the continuous removal of groundwater, there would be settlement. So when the high-speed rail was built in those areas, we have, or the engineers has to deal with the problem of settlement. In fact, what they have done is they have stopped the removal of groundwater from the wells such that the settlement will be less. Okay, so that would be one example that we have within Taiwan. And then another example that we have seen that is associated with settlement would be the Kansai Airport in Osaka of Japan. So the soil deposit over there is relatively young. So they also have settlement issues. So the engineers over there have come up with several mitigation to help reduce the impacts of settlement to the airport. So what they have done is under each column they have put in a lifting jack. Okay, so when there is a settlement, they will have the jack to lift the soil up. Okay, so in that way, the problem of differential settlement would not affect the performance of the airport. Okay, so that would be two examples that we see in Taiwan and then also in other countries that is related to settlement. So today what we are going to do is to perform a consolidation test. Basically what we are going to do is use this consolidometer. Okay, so what you are going to do is to place a specimen in this device, and then we will try to observe how much settlement that will be induced to the specimen per certain amount of loading. Okay, so if you look at this graph here, this will be the loading history that we are going to use for the upcoming 2 weeks. So the lab that we are going to perform will last for 2 weeks, mainly because during each load increment we have to wait a day, okay, for the consolidation to complete. Okay, so that's why we will have to wait for 2 weeks for the lab to complete. So if you look at this graph here, okay, we will start from a load of 0.5, and then for each load increment, basically it will be double of the previous amount. Okay, so during the first loading stage, we will load from 0.5 kilogram to 1 kilogram. So from here to here, we will need to wait a day before we apply the additional loading. And then we will keep doing that until we have 16 kilograms of loading. After we have reached that, we will unload, okay, unload back to 0.5, and then it will take several days as well, because we also need to wait for the soil to swell when you unload the soil, and then we will reload again, okay, and then this time we will reload up to 16, and then after that we will load it to 32, which is larger than the maximum loading that we have, which is 16, okay, and then after we have reached 32, we will unload the soil back to zero loading. Okay, so this will be the loading history that you are going to use for this lab. So in each load increment, what we would expect is you can evaluate the relationship between settlement and time. Okay, so what we want to evaluate or come up with is a parameter called C sub v. C sub v is the coefficient of consolidation. In your soil mechanics class, your instructors should have discussed two methods that we can use to figure out the parameter CV based on two fitting methods. One is the Taylor's method. Basically, he will plot, okay, what you have to do is to plot sediment versus the square root of time. So that would be Taylor's square root of time fitting method. So from this, you will evaluate Z sub B. And then and there is another method which is called the Casagrande logarithm of time fitting method. So this time you will plot sediment versus time, and then the time will be in log scale. Something that I forgot to mention is when you place your specimen in this consolidometer, we will try to be close as close as we can to simulate the situation in the lab. So for example, in the field, okay, you may have a sand layer, clay layer, and sand layer. As what I said previously, sand will have a higher hydraulic conductivity than the clay. So what we usually do is we will evaluate the coefficient of consolidation for the clay. So when you prepare the specimen, you will have to somehow simulate this situation. In the field, what you will expect is, okay, if you have applied loading P to the site, the water in the clay will escape through this two-way drainage path. So in the lab, what you will have to do is you will have to mimic this situation. The way to do it would be we will put a porous stone underneath the clay specimen, and then another porous stone above the clay specimen. Those porous stones would be used to simulate the sand in the field. And then those porous stones can have similar hydraulic conductivity as the sand in the field. Okay, so what I'm trying to say is when you prepare your consolidometer and then also the setup of this test, you would try to simulate as close as we can to the site condition. All right. So after you have performed this load on your specimen, what we want to calculate or evaluate are two additional parameters. Okay, so this time what you want to plot is your load, okay, your pressure or your pressure that is applied to the specimen. And then here would be your Foy ratio. What you would want to do is you will have to combine all the results that you have for those loading and unloading and reloading stage. You will plot this graph. So basically what you expect to see is for the first loading stage from 0.5 to 16, you will have this curve here. Okay? And then when you unload from 16 to 0.5, you will have this unload curve, okay? And then when you reload again from 0.5 to 32, okay, basically the curve would approximately look like this, okay? And then once it reaches 16, it will continue with what you have previously. Okay, so this is the loading stage, unload and reload, and then after it hits 16 kilogram, it will continue with the previous curve again. Okay, and then lastly, you will have to unload. Okay, so why do we want to plot this graph? Because we have to evaluate two parameters. One is this, okay, one is this, that would be C sub C. And then another parameter will be the C sub S. C sub C is called the consolidation index, and then C sub S is the swelling index. Basically what you would expect is C sub C would be 5 or 6 times larger than C sub S. Why do we have this? Because soil has memory. Okay, soil has memory. If soil has been subjected to certain amount of loading in the past, what you would expect is during that reloading, the amount of sediment will be less. Okay? Once it hits the past maximum stress, it will follow the previous C sub C, the slope of C sub C again. So the sediment in this region will be much higher. Okay, so we will utilize all the results that we have for the next 2 weeks to come up with this plot to evaluate the swelling index and then also the consolidation index for the clay material we have in this lab.